And we start with a review talk by Sakura Schafer-Nameki, and she's
and it goes to, oh, amazing.
So she's going to talk about generalized symmetries.
It works, yes, yeah. Sorry, I wasn't paying attention. Yeah, okay, sorry, he was telling me something. Okay, thank you very much to the organizers, to my chair, for introducing me, and for inviting me to give this overview talk to this absolutely stunning place. I mean, it's really a fantastic campus here. It's very nice to see sort of everyone come to this location. You might note that there's a slight change in the title, but now you're in this room and it seems the doors are locked, so you can't leave. And I changed it to categorical because it's, you know, it used to be generalized if you didn't read the title, because I think it's important that we get used to this terminology because it's going to stay with us. And one of the things that I would like to convey in this talk is it's nothing mysterious, it's nothing strange, and something you should learn just like the way you've learned group theory. So what is a global symmetry in 2025? Well, if you ask the generic person in this field, they will give the answer. It's a fusion higher category. But this is literally just a statement. Take your favorite quantum field theory or quantum system and look at all the topological operators of any dimension. They can compose in a particular way. And that's the thing that will form this kind of gadget. Here I'm talking about finite symmetry. Is this working, by the way? Okay. Finite symmetries, so not continuous ones. They should be included into this, but for finite symmetries, this is the answer. So a quick recap, if you've sort of, not paid attention the last 10 years on this subject. Of course, in 2014, the first generalization was from standard global symmetries acting on point operators to higher form symmetries acting on extended operators like Wilson lines, Toft lines, and so on. But then in the last 2 years, there are these so-called non-invertible or categorical symmetries, which compose beyond the sort of group-like composition. In particular, they don't have inverses. So that's why they're called non-invertible, and it's really synonymous to this categorical language. They compose, you take a p-dimensional object, you compose it with another one, and out comes a sum with some coefficients. They could be integers, but they could also be actual partition functions of theories. So this is the generic structure that we see in topological defects when they compose in the generic quantum field theory. There are many reviews and there are many high energy focused sort of overview talks. There was one at Strings this year. There was one in 2023 by Shuhang, and I gave it one last year at Strings, giving also some view on how these are realized in string theory. I realized this is Eurostrings. Now I'm going to declare I will not talk a lot about string theory. Andre will not like this, because I think one of the most exciting things that actually happens in this field is that there's been an enormous, really stunning kind of synergy between all kinds of fields that until, maybe a few years ago were relatively disconnected. High energy, condensed matter, math, quantum info, and AMO. And if you don't know what AMO is, it's atomic, molecular, and optics. And literally, through these symmetry structures, these things have sort of come together. And there are questions that you ask in one field, you answer it, and then you can use that to answer other questions in these neighboring fields. And I want to explain to you how this works, and in a particular instance. Let me just sort of, of course, each one of these blobs have their own agenda, but let me sort of just quickly talk you through what these people are after, and we know what we're after. We want to understand global symmetries and their implications. In math, they're interested in the theory of such things and the classification, and I think the most exciting sort of new result is that there's basically classification of all symmetries, discrete symmetries, in 2+1 dimensional systems. So that's sort of a math output that is extremely useful for us, and you can use it to study 2+1D QFTs. I won't go into details. You'll have the slides later. You can look at this. In condensed matter, of course, people are interested in phases of matter, phase transitions, lattice systems, so that you actually can, do numerics on them, simulate them. And in fact, there's been a lot of interesting work independently on these categorical symmetries in such lattice systems, developing numerical methods, but also trying to understand what are actually anomalies of such things. And of course, as a high-energy physicist, we're also interested in anomalies for such symmetries. Then there's this field of QI and AMO, and there are loads of questions that, to us are a bit more alien. So they want to construct a fault-tolerant, error-correcting universal quantum code and can be implemented in some future, near future, hopefully, quantum device. So there are all kinds of things that we might not connect directly, but at the end, I hope to convince you that some of the theoretical things that we do actually play a role there as well. Okay, so you might still think secretly, sitting there, well, this is still exotic, physically probably useless, niche subject for theorists somewhere in high energy. And I think basically after this talk, I hope you will get some idea that that's not the case. So the first thing I want to do is give you a reminder, what are the constructions? And they work in any dimension. You pick your favorite dimension, and I can give you a construction of non-invertible symmetries in quantum systems that you could study. So this is like a universality kind of thing. They're like these kind of structures. But then actually there's the second part where I really want to show that there's a concept, a theoretical concept that's very familiar to high-energy physicists that can then be used in all these interactions. And the first thing is to actually classify phases. And there are pure state phases and mixed state phases, so also noisy systems can be studied. And then study of anomalies. So anomalies like Toft anomalies, they constrain RG flows for such categorical symmetries. And finally, there's some direct connection to these quantum simulators and actually constructing some new interesting codes. Okay, so let's recap what we know about non-invertible symmetries in high-energy physics. So this is setting the tone, like where these things actually occur. And the classic example is coming from, if you have a system that has a self-duality, this is a vehicle to construct a non-invertible symmetry for you. So the canonical example is the Kramers-Vannier duality in, for example, the Ising spin chain model, a transverse field Ising model. And at the critical point, the Ising CFT has a symmetry. When I square it, it squares to 1 plus another symmetry generator that's a Z2 symmetry. So that's a canonical non-invertible symmetry composition. So how do you see this in the spin model? Basically, you send G to 1 over G and this ZZX kind of transverse field Ising model, and it maps basically these two terms into each other. That's not a symmetry for generic G, but if G goes to 1, it becomes a symmetry, and that's precisely N. Now you can play this game also in any other even dimension. In particular, this is what kicked off this whole field. Namely, in 4 dimensions, space-time dimensions, we can look at a self-duality symmetry of quantum field theory. And when we do that, we can look at if the QFT is equivalent to the QFT after the duality. We can construct completely analogously to this a non-invertible symmetry for the QFT. Right, so this is the canonical example is, for example, if you like supersymmetric field theories, you can look at SO3, theta equals to pi, and that'll have that kind of symmetry defects. But it also works in any even dimension. So you could also say, well, it also works for the 6D theories. And indeed, in 6D 2,0 theories, you can construct, now using self-dualities of 6D theories, which are Green-Schwarz automorphisms. So they map the BPS string charge lattice into itself. You need to compose it with some additional topological things like gauging the 2-form symmetry. Right? So here this was a 0-form symmetry. This is a 1-form symmetry. And this is now a 2-form symmetry. So it's always the one that when you gauge it, it goes back to the same degree of form. So in this case, it's a 2-form symmetry, goes back to itself. You can construct non-invertible duality defects. So one example is the SO8 6D theory that can be made into good quantum field theory. And this has sort of an S3 worth of non-invertible defects, which you compose from these Green-Schwarz automorphisms, which are in these black arrows, and then also some topological manipulations. And any loop that you form here will give rise to a non-invertible defect. So when you compose that with itself, it'll give a non-invertible fusion. So in fact, right, this tells you in any even dimension you have a self-duality, you could construct these kind of non-invertible symmetries. Another example is if you have an auto-automorphism like charge conjugation, then you can gauge that and you also get a non-invertible symmetry. So the simplest example is in any dimension, the O2 gauge theory. You start with U1 and you gauge the charge conjugation. Basically, if you look at, say, the U1, so it has these kind of topological defects. I'm agnostic about the dimension here, but basically what charge conjugation does is it changes the alpha to d minus alpha. So the invariant combination is a sum. And now, even naively, if you calculate the square of that, it'll be the sum of other terms. It's a little bit more subtle than that, but that's morally speaking what's happening. So whenever you have, for example, charge conjugation, you gauge it, you get a non-invertible symmetry. And then finally, the one that you probably all have heard in phenomenological applications also is whenever you have an ABG anomaly, be that, you know, in some QED, or it could also be with an anomalous R symmetry or something, then you get a non-invertible symmetry. So here you have basically a non-conservation equation. That's the ABG anomaly. So the right-hand side spoils the conservation of this current. You can sort of reinterpret it as saying there's now a symmetry where I sort of shove this back to the left-hand side. I declare the symmetry generated as not just exponentials of this star J, but I stack it with some additional TQ of T. And when I do that, then this here is now closed because it satisfies exactly this equation, but it comes at the price that this now is non-invertible. So if I compose it n with n dagger, it gives something that's not the identity, but what's called a condensation defect. So whenever you have an ABG anomaly, you can also equally talk about a non-invertible symmetry. Okay, so these are basically 3 examples of how these things occur in your favorite QFTs. Now, one criticism is all of these things are kind of obtained by gauging, so how come they have some physical implications? So I want to convince you that there are some interesting physical implications that you wouldn't have known had you not studied these symmetries. So the first one is this so-called modified crossing relation that goes back to this paper here by Copetti, Cordova, and Komatsu. And it's really sort of a hallmark of if you have a non-invertible symmetry, you can't just do your standard rules of, you know, scattering and say in some integrable systems, but you actually need to modify that. So the idea is if you have a 2D CFT, a rational CFT, it has these non-invertible so-called Verlinde lines. These form one of these categorical structures. And if you now have a relevant deformation that preserves some of these to an integrable theory, so massive theory, then in fact the scattering gets modified by the consistency with that symmetry. So what they found is that basically if you have this sort of standard scattering of kinks in these theories, then the Ward identity with these symmetry generators imposes that now there's not a standard crossing relation, but gets modified basically by this fraction, this quotient of dimensions of these topological defects, which doesn't have to be 1. So this is a sort of really changing how you solve crossing. There's also a similar thing in this paper by Minwala and others in 2+1D, where they scatter anyons, so one-dimensional topological defects. So this is clearly a very exciting area to explore further and see what kind of implications we get. The other implication is, so if you have a non-invertible symmetry, you can ask, it's a slightly more condensatory question, but it also is something you can ask about, you know, phases of quantum field theories. Namely, when you have non-invertible symmetries, do they need to new IR phases and phase transitions? And so canonically, we would say, well, if you have a group symmetry, then Landau taught us, well, you know, any second order phase transition is basically given by some symmetry breaking for group G. And I'm taking G to be a finite group here. So the gapped phases are where G is spontaneously broken to a subgroup. Right, so this is literally one-to-one from the sort of Landau story, so some subgroup H. And any phase transition is a Landau phase transition if there are two subgroups Hi, and they classify this, they correspond to these gap phases, and then there's a transition if one is a subgroup of the other, and then the order parameters are basically sort of trivial under one and non-trivial under the other. That drives this transition. The question is, when you have a categorical symmetry, how do you now extend this to, what are the rules here, where this also is sort of specialized back to this group-like case. And so for this, basically, now many of these words will not be clear yet. We will get to this, but I want to just illustrate, this is a pretty sharp, simple sort of summary of how Landau transitions work. If you have a category S, some non-invertible symmetry S, in particular, this is very clear for 1 + 1D, then the gap phases are in one-to-one with what's called gap boundary conditions of the symmetry TFT, or so-called Lagrangian algebras of the Drinfeld center of S. So this is generalizing, there's a subgroup of a group, and that's sort of the unbroken subgroup. And then the phase transitions are basically, you have two of these algebras. If they intersect and there's a consistent algebra, then there can be a phase transition between these two things. And that generalizes this statement that one group is a subgroup of the other. And the order parameters also come from particular types of topological defects in the system. So it's extremely clear, parallel to the system that we have for groups, but now for categories. Okay, so this is just to say, first of all, in d-dimensional quantum field theory, you can construct these non-invertible symmetries, and we've seen some, very sharp predictions of these two things that we didn't know, and so they seem extremely worthwhile studying. But the story is even better because there's all this synergy with other fields. And so I put down these blobs in the following because it sort of is something that comes from this high energy thinking. It's actually very closely related to holography. A lot of you are working on holography, so maybe that perspective is very helpful for this. But it goes into quantum, condensed matter and quantum info. And then also anomalies, of course, are relevant for all these fields. And then finally, there are these applications to these codes. And all of these three things, they all are sort of tied together with one thing that I would like to explain, and that's sort of the thing that I would like you to take away from this talk, namely what is the symmetry TFT, and sort of this, there's sort of some synergy through this principle of the symmetry TFT, essentially having different incarnations in different fields and being extremely useful. So we'll talk about what that is. So the symmetry TFT is also called often the symmetry sandwich because of the structure of two slices of bread and some filling. And then in this paper by G and Ren, they also call it topological holography. It's closely related to holography, but it's really, for a high energy physicist, I think the wrong terminology. Because what is it? It's basically you have your theory T with some symmetry S. So S is a finite symmetry, but it can be non-invertible in d dimensions. And the symmetry TFT is just gauging that symmetry in d+1 dimensions. So if you have a group symmetry, the sim TFT is just a finite group gauge theory, a Dykov-Witten theory in d+1 dimensions. But more generally, it's some more complicated topological field theory. If it's for 1 + 1 dimensional system, so the boundary is a 1 + 1 dimensional theory. Here, let's start here with this theory, this 1 + 1 dimensional theory. Then, in fact, the bulk will be 2 + 1 dimensional. It's what's usually referred to as topological order in 3 dimensions. And the topological defects of this are called anyons. So they're like lines, but they don't have necessarily spins that are either bosonic or fermionic. It can be any value, any fractional value. So that will be one of the setups we'll be discussing in some more detail. But what's sort of the paradigm here? This is this picture. So the SimTFT is basically this theory with the symmetry action S is equivalent to this 1-dimension higher TQFT on a slab with 2 boundary conditions, One boundary is realizing the symmetry. So all the symmetry defects live on there. So if you take all the topological defects and you push them to this boundary, they generate the symmetry S. And on the other side, you have all the dynamics. So here you put your n=4 super Young-Mills, or your favorite quantum systems and lattice model. And on this side, you actually put the symmetry defects. And in the bulk, you have this full TQFT propagating. And what is sort of the utility of this? It sort of separates the symmetry aspects from the dynamics. So everything you want to know about the symmetry can be studied essentially from this, usually ignoring this boundary. So there'll also be these things, these defects that stretch between the two boundaries, and those become charged operators in the actual theory when you collapse this back down, right? There's a TQFT, so the size of this interval is completely immaterial. You can collapse it, and you get this back this d-dimensional theory. And the statement is these two things are equivalent. So these charges are basically topological defects stretching between both, and the charge is calculated by looking at how topological defects braid in this TQFT, how they link with each other. Okay, so that's the sort of bare bones summary of the SymTFT. To actually do these three steps, these three applications, we need to extend this a little bit and look at sort of this sort of double sandwich, or this club sandwich. So we have now 3 slices of bread and fillings. And now the question is, so here I have the SymTFT for symmetry S, and now an interface to another SymTFT for another symmetry S prime. And I always want to think of this as basically a larger symmetry, and here there's some reduced symmetry S prime. So these kind of interfaces can come from what's called the condensation of defects. So essentially, I will define certain ends of topological defects. They will end and some will propagate through. And so this is sort of after condensation, the reduced topological field theory. So if you study this system, and you really just need to understand, say, 1 + 1D, what's going on with this, then we can apply it to these 3 things. And it's always the same math applied to 3 different physical systems. And it's sort of a pretty cool application of this thing. So it's sort of a buy 1, get 3 for free. What is this sort of club sandwich? Well, really, it's about this interface, right? So the interface is telling us how these 2 topological field theories are connected. And let's stick to 1 + 1D. So then these are topological lines. The bulk is a 3-dimensional TQFT, here and here. And now these lines can do various things. They can either end, they can go through, or they can just bend down. They can't end, they can't go through, so they just confine. So these are the 3 scenarios. One is the anion ends. That actually defines the interface. So the interface is sort of given in terms of the lines that can end on it. So that's the condensation of anions. This is usually given in terms of a sum of particular integer linear combinations of such topological lines or anions, and they have to be mutually local. You can't have them end and not be mutually local. So this locality is basically what means condensable algebra. Then there are the ones, if you take them in, and then they can't end, but they can't go through because, in fact, they braid non-trivially with these red ones. So these yellow ones, basically, they're not mutually local with the ones that end. So they kind of just stick around and they bend down and they confine on this interface. And then finally, they're the ones that can't end, but they sort of go through. They're the deconfined ones, and they define what is this reduced TQFT. If S prime is trivial, this is nothing other than a gap boundary condition. It's just an interface to the trivial theory. So the case of the standard SymTFT is sort of packaged into this as well. And in that case, this algebra isn't just sort of mutually local, but it's also maximal, and these are called Lagrangian algebras. So studying Lagrangian algebras is basically studying these interfaces to the trivial TQFT. Okay? So this is the picture that you should keep in mind when I'm talking about these interfaces. And now we can look at examples. And the first example is for groups. So if you have a finite group, you can ask what is sort of the TQFT that lives here? What are these type of interfaces? So for finite group, the SymTFT defects are labeled by conjugacy classes and irreps of the centralizers of elements in this conjugacy class. And that's important in particular if the group is non-abelian. If it's abelian, I'll give you a much simpler description of this, but essentially this is sort of the structure of these defects. So each one of these lines here is now labeled by that kind of data. And the question is now, what are these mutually local things? So they all braid around each other, and there's a complicated structure. And basically, one can classify these condensable algebras, these interfaces, also if the group is anomalous. And they're basically given in terms of subgroups, normal subgroups of the subgroup, and some additional cocycles. And this is basically where also this whole thing will connect back to this original Landau story. One example is, of course, if I take all the irreps, so the identity conjugacy class, meaning the whole group, and the irreps of the group, if I take this to be the algebra, then this is just an interface to the trivial theory. It's a maximal thing, and it's on this interface we realize the group G. Right, so we have lines that are in the irreps ending. The things that talk to this, that braid non-trivially, are the group elements. So in fact, on that boundary, we generate the group G. Vice versa, if we take the conjugacy classes with the trivial irreps, then we generate the dual symmetry, which is rep G. So the irreps of the finite group G, they also form a non-invertible symmetry. So this is basically non-invertible for non-abelian groups G. Okay, so I can see some eyes glazing over, so let's actually think about this for Zn. There's no funny non-invertibility, but it might sort of explain a little bit what these things are. So if I have a Zn zero-form symmetry in 1 plus 1D, so for example, Z2 in some two-dimensional QFT of your liking, then the SymTFT is basically just a Dicke-Witten theory for Zn. So it has background fields B1 and the dual field A1 and B1. And there are topological defects, which are just the holonomies of B1 and A1. But because of this BF term, they will braid non-trivially. Right, so each one, E to the N and M to the N is 0, but it is 1, excuse me. But when I exchange them, because of this BF term, they will pick up a phase, and it's given in terms of the linking of these gamma 1 and gamma 2. Right, so these are some loops, and now if they sort of link, they will give a phase, and basically this is how we measure that this is sort of a system of now lines that are not mutually local. And these gap boundary conditions that are sort of giving the group symmetry and the dual symmetry are just now take all the E's, all the powers of E's and all the powers of M's, and they generate the Zn or the dual Zn symmetry. In this case, the representations of Zn are, again, isomorphic to Zn, so there's not much interesting stuff happening. But now you should imagine, for the non-abelian case, that's not true. In fact, in this case, you get this non-invertible symmetry from that boundary. Okay, so that's sort of just to put this into context. And then now, of course, other algebras, which now give interfaces that are, for example, sums of E's to a certain power only. So for Z4, it could be 1 plus E squared, for example. And they're classified by the subgroups of the group that you started with. Okay, so that's sort of how this fits in. And now let's apply this to the phases. So first question is, can we classify pure state phases? And the answer is yes. Basically, the SymTFT sandwich, we start with a symmetry, we put the symmetry and the symmetry boundary, and then any other sort of physical boundary that's sort of describing the dynamics, which now is a TQFT, so it's again a gapped boundary condition, will give rise to a gapped phase with that symmetry. So classifying the gapped phases is one-to-one with classifying these gap boundary conditions of the SymTFT. So, and you can get all kinds of things. You get spontaneous symmetry breaking phases, and then these local operators that come from these stretched line operators, they give rise to the charged operators, and they give also the transformation under the remaining symmetry, the broken symmetry generators. The special instances when you have only the trivial operator stretching, that can be a trivial phase, or what's called a symmetry protected phase. So there can be sort of not local operators that are order parameters, but string-like order parameters. And those you would get by ending a line here and then stretching it down. So it can't end here, but it can sort of do this kind of L-shaped configuration, and you get a line operator that's attached to a point as an order parameter. Then this is just to tell you, this is literally, you can put this into work. So the simplest case is when you have a representation now of the simplest non-abelian group, S3. There's a two-dimensional irrep with this non-invertible fusion. 1 minus is the sign irrep, and E is the two-dimensional irrep. So this is a sort of a very straightforward, decompose the irreps of S3 into the tensor product of irreps back into irreps. And there are, from this analysis, 4 gap boundary conditions, and these are the associated phases. So you get the number of vacua read off from the number of lines that can end, and then the symmetry action from the braiding with the other topological defects. Okay, and then there's also a story about the phase transitions, and that's now where we use this club sandwich with an interface. And here the idea is very simple, that if I have a SymTFT for symmetry S, like some categorical symmetry, and an interface to another smaller symmetry S prime, I can construct out of phase transitions for S prime, phase transitions for S. So that's essentially this kind of this map between these TQFTs allows us to do that. So that's sort of how we then model the phase transitions. I actually don't want to discuss this more because I've talked about this on several occasions. I really want to get to these new applications, which are a little bit less in the high energy sort of comfort zone, because they really answer things that we may not be immediately interested in, but it sort of uses exactly the same technology. So mixed state phases is sort of another question, right? So you have, usually in your lab, you don't have sort of a nice pure state, but it's noisy, there could be at finite temperatures, so there could be all kinds of things that disturb the system, and you still would like to kind of describe what kind of phases you can have. And for this, one needs to understand mixed state phases and sort of what kind of constraints can symmetry still give in such a context. So here we don't have a sort of just a Hilbert space with some pure states, but now we need to talk about density matrices. So we have some Hilbert space H, but now some operator psi like this, and it satisfies rho squared is rho, then it's just a pure state, but normally it won't satisfy this condition. And it's Hermitian, so this is going to be an important condition. So the question is, if you have a system that's only described in terms of such a mixed state, it can also happen by the way in holography. There are many systems where you have this, of course. What can symmetry still tell you about that? So symmetries in mixed states aren't sort of as sort of sharply defined as in the pure state case. We just act on the state and you want it to be in some representation. There are two notions. One is called a strong symmetry. So here it says you act for a group symmetry with a unitary on you take the product with the density matrix, and it's just a phase times the density matrix. And then there's a weak symmetry where you need to conjugate. And of course, a strong symmetry is also weak, but a weak symmetry need not be strong. So now these two slightly, refined notions of symmetry, and that sort of works for invertible group-like symmetries, which are realized in terms of unitaries. For non-invertible symmetries, you have sort of some fusion, and here I'll assume it's something like S as dagger is 1 plus some sum of other defects here. So you have basically the structure, it goes to identity plus some other stuff. Then you actually can write this in terms of the strong and weak symmetry thing is basically a statement about you act on the left with this, or you conjugate and you get phases in both. Here a phase and here the mod of that phase. Okay, so that's sort of the kind of structure which now would like to study the phases of. So one trick how to deal with density matrices is to actually purify this, so actually map it to a pure state. And that, of course, comes with some constraints. You can't just map a mixed state to a pure state. Here, basically, you flip this cat into the bra into a cat, and you get psi bar now in a double Hilbert space. And this kind of state, you could now ask, what is the notion of strong and weak symmetry? So the strong symmetry now says you have now two Hilbert spaces, a left and a right. Strong means you can act on the left, and it needs to be essentially invariant, or on the right, it needs to be invariant. And the weak symmetry says you have to act with both at the same time, and then it needs to go back to itself. So this is sort of now a way of entering now this pure state classification into this mixed state business by purifying to this doubled Hilbert space. And of course, once you are at that point, you can then also extend this to in this purified state, also is called the choice state. So you can now look at the SymTFT classification of these kind of mixed states. By looking at now the doubled symmetries, you have a left and a right symmetry, and there's this sort of funny thing that in fact you hear complex conjugated. Now there's some symmetry where if you switch them and you bar, so you swap star, it needs to be a symmetry of this density matrix, purified density matrix, so these symmetries actually need to satisfy this relation. So now the question is, if I have this pure state classification for phases, can I now also get the mixed state classification? So which boundary conditions of the SymTFT for this doubled symmetry give rise to strong symmetries, to weak symmetries? What kind of properties are there? And also, is any phase of the SymTFT also a mixed state phase? So there were actually two groups in the condensed matter quantum info working on this for group symmetries, and we did this for categorical symmetries, and we put this out in the same day, and we all looked at the same. It's all basically the same idea that you double it, and now you can actually describe these mixed states, but it comes at a particular cost, because not every symmetry Lagrangian, so gap boundary condition, is in fact giving rise to a density matrix once you go back to the reduced Hilbert space. So only certain Lagrangians, they have to be invariant under this swap star symmetry, and they need to give rise to positive definite density matrix. So there are conditions on this that then actually give you a more refined or smaller set of phases that are consistent for these kind of systems. So these mixed phases basically now come from looking at Lagrangians that don't factorize into left and right. And the interesting types of phases are that you can break a strong symmetry to a weak symmetry, but you can also break now a strong symmetry to a weak symmetry partially and have sort of a trivial phase. There are all kinds of now mixed strong, weak SSBs and SPT kind of phases that sort of enrich this symmetry classification. So just to give you an idea of how this works for Z2. So these are basically, back in terms of the sort of density matrix formulation, a strong symmetry basically that's unbroken satisfies this kind of relation, and we can translate that into the SymTFT. For Z2 strong symmetry, this is a simple sort of exercise of these left and the right anyons, now M and L, as I introduced earlier. And then there's one that doesn't factorize, and that gives sort of this phase is basically you have this strong Z2 symmetry, and the weak gapped phase has only this anion that's sort of diagonal. So this means the E anions basically don't exist on their own as E left and E right, but actually only in this combination. And so that indicates a strong to weak SSB phase. Okay, so from just the SymTFT, we can read off what is the property of the phase that we get in this after collapsing this back to a two-dimensional system. Okay, so for groups, this is not that interesting because you could study it also in other ways, but now we can we can apply it to this RAP-S3 again, for example, or any other non-invertible symmetry, and you get now these phases that are mixed, strong, weak, symmetry breaking phases for RAP-S3 that sort of model somewhat the pure phases, but actually have a slightly more refined breaking pattern because you could go from a strong symmetry to a weak symmetry and so on. Okay, so that's basically the let me maybe, so there's also, okay, so I should talk about this very briefly because I promised that this sort of sandwich picture will resurface in each of these topics. Essentially, if you want to start with a symmetry that's weak, so it acts at the same time on the density matrix from left and right, then you could model it in terms of starting with a strong symmetry and sort of condensing to a diagonal symmetry. So very similar to how I did this thing with this here. This is basically going to a weak symmetry now because you get this diagonal anion stretching here. So essentially, you can model a weak symmetry by taking the SymTFT for the double, for the strong symmetry, then condensing sort of a diagonal and going to the weak symmetry generators. So essentially halving sort of your SymTFT. The interesting thing here is that not every symmetry that you put in here can actually be made weak. So this is easy to see that if you have generic fusion rules of this type and you have this weak symmetry condition and then you want to make these compatible, then you run into a problem just sort of, plugging this in twice. You get this here, but it also needs to be that. And the fusion, he'll give all these terms. And so now you need to have relations that, in fact, you tell you what is WC with rho, WD dagger. So in fact, you can't make any non-invertible symmetry weak. And in fact, so one nice class of symmetries where you can make at least part of the symmetry weak are these sort of like the Ising symmetry category. So here, basically, there's a non-invertible defect n that fuses n squared to 1 plus the Z2 generator. And we can make n weak and keep the Z2 strong. So what this basically means is that on this side here, all of these become just some factor times rho. And on this side here, you still have this non-invertible generator. And so this gives you from what's called, so Ising is just what's called the Tambayamagami Z2 category. You might have heard of this. If not, then there's now, for any abelian group, there's essentially a duality symmetry, like I explained at the beginning. And if you use that, you can get for any abelian group a Tambayamagami symmetry. And in fact, when you do this construction of making the duality weak and keeping the Z2 strong, you get a Ty Z2 Z2 as this reduced order on the right-hand side here. Okay, so that's sort of applying these things to phases of various making, pure state phases, mixed state phases. You might ask, do you actually really get interesting new phases? Like, 1 plus 1 dimensional phase is a little bit boring. That's just a, number of vacua and maybe some relative Euler terms. So in 2 plus 1D, you can apply this and get some genuinely new phases in the sense of there could be a vacuum structure for a non-invertible symmetry where you have two sort of universes. They're exchanged, so they're partial SSB phase, but then each of these have a different topological field theory in it. So you have two vacua, SSB phase, but each vacuum has a different TQFT. So that's a very exotic kind of phase that hadn't been seen before, and it's interesting to study what these could be used for. Okay, so let me head to the third application, and this is something that I think may be closer to everyone's interest because it's about sort of RG flows. And again, I will tell a story, and then in the end, we'll use the sandwich to solve the problem. So this is a very useful investment to learn about these sandwiches. So we all like Toft anomalies because they constrain RG flows. If I have a theory in the UV and I want to go to the IR, what do? I look at things that I can track through the RG flow, and Toft anomalies are one particularly strong kind of tool at our disposal. Now, usually, we have for group-like symmetries, we can really quantify what is this anomaly. There's some cohomology class or something. But when it gets to categorical symmetry, it's more coarse. So it's more like, is the symmetry anomalous or not? It's a yes-no question. And in mathematical terms, this means is there what's called a fiber functor. It just means, can you trivialize the symmetry? Is it non-anomalous? Can you make it trivial in DIR? So one thing that obstructs sort of this being a very simple exercise, Toft anomaly matching, is that there's sort of three things that can happen, in particular in higher dimensions. The symmetry might just trivialize. in the IR, or there can be new symmetries that emerge in the IR, or there can be really more strange things like what's called fractionalization or transmutation. So symmetries of a particular degree don't stick to their degree. So a zero-form symmetry can transmute to one-form symmetry or something. So these are kind of things that mix up the game and make it more complicated. And for non-invertible symmetries, it's even more stringent because there it's not even clear what's a symmetry, what's an anomaly. There's, as I said, this criterion, the fiber functor, which just says if you have a category and you have a map to the trivial symmetry, and that satisfies some criteria, then that's actually telling us it's non-anomalous. But it doesn't tell you if it's anomalous, what is the anomaly? Right? So that's what we would like to quantify. What are these Toft anomalies? So what we did with my two postdocs, Andrea and Christian, and my student Johan, is to actually formulate this kind of anomaly matching, to actually quantify what that is. In particular, in 1+1D, this can be made completely precise, and I have lots of examples in higher dimensions. And again, the symmetry TFT plays an important role. Now, these pictures, they look like symmetry TFTs, but they're not. Okay, so now you better pay attention for a second, because this is not a symmetry TFT picture. This is just a quantum field theory. This is a QFT, and this is the space-time, and there's no sandwich here. So a global symmetry basically is made out of topological defects, so they should be robust under the RG flow. And indeed, Guyot already noted that if you have a theory in the UV, and here there's some topological defect, and you do on one half space a relevant deformation, and then you flow to the IR, right? You get this half space sort of interface and an RG interface, and that our interface models sort of the RG flow. So for groups, we can now track what happens to these topological defects very easily. Namely, I have a map from the UV symmetry to the IR symmetry, and basically they have to satisfy some H3 cohomology class, for example, with G, U1 valued, and the pullback of the IR symmetry needs to be the UV symmetry anomaly. So for categories, what we're proposing is, what replaces this, is there needs to be between these two categories a particular type of map which has to satisfy consistency with the composition of defects and various other consistency conditions, and mathematically it's called a tensor functor. So what basically RG interfaces should correspond to are tensor functors. So when you have a UV theory and an IR theory, and you go with your topological defect through this RG interface, D maps to this F of D. Okay. Now, that's sort of telling us how symmetries would map, or how two sets of symmetries could be consistent with UV and IR. It doesn't tell us yet what is actually the measure of that anomaly. And for this, we need to look at a short exact sequence of such functors. So C is our symmetry category. And now, like with groups, you can embed a category and you can project. And basically, if this is sort of such that the image of I is the kernel of P, it's a short exact sequence. And if it's exact, it implies that N, and I can map N all the way to trivial. So N is anomaly free, right? Because N can map to a trivial category, so I can trivialize it. So in fact, if I have a C and I have such a sequence, I can trivialize N. So N is always the bit that's, in the RG flow I can wash it out. Whereas S can potentially be the non-anomalous part. And so in fact, if you pick N to be maximal, so there's no other N that can sit there that's contained in a larger N that can sit in such a sequence, then we basically have sort of the maximal core of the anomaly on the right-hand side. And we call these things, these anomalous simple categories, or ASCIIs. And so they're basically the measures of the anomaly of that categorical symmetry. So you write down C, and you need to find N and S, and that's quite complicated and super annoying, and you don't want to do any of these mathematical manipulations, but you can recast it in the SimTFT, and then it becomes a very simple kind of exercise in these algebras and condensations. So this is our RG interface. So this is our space-time. Now I basically pop out the SimTFT there's a symmetry boundary now in the front, the physical boundary in the back, and this is filled. And this is the purple bit is what became of the RG interface. And I can project it also down, and then I get this picture of here's the SymTFT for the UV, for the IR. This is when I collapse it, the interface, and now there's a symmetry UV and a symmetry IR. And I want to understand what kind of things are now okay between what kind of symmetry boundaries can I put here that are then giving rise to a tensor functor. So a tensor functor basically gives, again, one of these interfaces in the SymTFT. And the rule is very simple. But this thing here gives rise to a tensor functor if and only if I slam it onto it's topological, so I slam it down to the UV boundary, it's equivalent to the IR boundary. That's the condition. And we can prove this quite generally. And now we can also do all these other things. We can do injective maps. It means that there is basically on this side here that all the ones that end on the interface, they basically also end on the symmetry boundary here. And the surjective maps basically means that these are so-called magnetic algebra, so there's only the trivial anion that can end here. And so then a short exact sequence becomes a SymTFT, now a triple sandwich. And we have the N symmetry boundary, the C symmetry boundary, the S symmetry boundary, and these guys are satisfying these conditions up here. And finally, the condition for this sort of minimal ASCII kind of thing is basically saying that if you have such a sequence, and now your category is such that it doesn't have any of these surjective maps into it, so basically there's no non-trivial magnetic algebra, then it's an ASCII. So that's a criterion that you can now check extremely efficiently. And since my chair is telling me that I have very little time left, I will very quickly tell you how it works for groups. Then I'll give a non-invertible example, and I'll leave the quantum info applications for the discussion session. So for group symmetries, we would like to reconstruct in this way this pullback of the anomaly class. So let's say we have a normal subgroup and the projection. Then in terms of categories, this means this. And now the question is, can we now, for example, see two different types of anomalous sort of cores of that symmetry? So if we take, for example, Z8 with anomaly class 4, so this is the class 4 and the H3 of Z8 with U1 coefficients. Then there are actually two sequences that both basically have the anomaly free part is a Z2, and then the projection is a Z4 with anomaly 1 or anomaly -1. And if you package this back into the SymTFT, it just means you get these kind of pictures. And indeed, there are two types of interfaces here that go to Z4 with +-1 anomaly. So this is just recasting stuff that we know for groups. But now we can also look at non-invertible symmetries. Right? So there I don't know what is an anomaly. But what I know is that I should be able to sort of trivialize everything except for these ASCIIs. So the ASCIIs are these sort of core bits of anomalous symmetry. So the first example would be easing, but easing is itself an ASCII. So that's sort of actually a minimum building block that you could use to build anomalies for some categorical symmetries. So the next one is these Tambayagami Z4. So here you have n squares to all the generators of Z4, right? For Z2, it was the generators of Z2. And there are two types of such SymTFT configurations. Both of them, again, trivialize Z2. In the middle, we have the Tambayagami Z4. And when you look at what type of interfaces you have to project onto, so these are now ASCII components. There's a Z4 with omega-1 and a Z2 with a mixed anomaly. So it means you can, in this non-invertible symmetry, trivialize the Z2 along the RG flow, but you will always either have a Z4 with anomaly 1 or a mixed anomalous Z2 left over. And that you can trivialize, and you need to match it in the IR. And of course, once you have this machine in place, you can apply it now to high dimensions. The applications that generalize the Wang-Van-Witten stuff, and then also fractionalization, also space-time symmetries. So this is basically the world is your oyster at that point. And because we have, you might wonder, why do you do it with the symmetry TFT? Well, first of all, I don't even know how to formulate this in high dimensions because we don't have enough structure in terms of what are these kind of interfaces, these tensor functors in high dimensions, and what are these properties of projective and injective functors. But we do know these interfaces, right? Crucially, the SymTFT is something we can also construct for, say, four-dimensional quantum field theories. So there's lots to explore. In particular, I think for continuous symmetries, where we also have the SymTFT, it would be very nice to actually understand how to construct such anomalous core contributions to the symmetry categories. Okay, 2 minutes. Okay, 2 minutes. So 2 minutes applications to, this is literally just to whet your appetite and tell you, okay, you can even talk to people that do lab physics. There are two applications. The first is we have all these phases, these new phases and phase transitions. Can one realize these in some actual, quantum simulators? And indeed, for example, this rep D4 symmetry, which is sort of like rep S3, but it has advantages that you can realize it on qubits. One can really write down a protocol how to put them into some cold atom lab and so realize them in terms of these Rydberg blockades. But a more theoretical, interesting thing is some of these higher form symmetries and also the categorical symmetries can be used in the context of improving our understanding of quantum codes. So one sort of direction is using higher form symmetries like Dijker-Witten theories for higher form symmetries, higher group symmetries. It's mostly done by Po-Cheng Sin and Ryohei Kobayashi and others. But then the other application is to what's called magic state preparation. And that's where our friend, the SymTFT, comes back. So there were 2 papers earlier this year which essentially use, again, this kind of condensation interface to construct what's called magic states. So magic is a technical term here. In this case, it just gives you a way to then do universal quantum computation. And what these people have done is, I will just show you the picture. Take the SymTFT for D4, embed the Z4 one with an interface. We now know how to do that. Condense it back down to Z2. If you pass a state that's what's called Clifford through this, you get a magic state for some non-Clifford gate. So, and that can be explored in many, many directions. And again, it uses literally the same kind of mathematics of these SymTFTs. Okay, so I hope it's clear that these symmetries are a very rich structure. There are lots of applications. I think the future, one of these things, one of the limitations maybe, or sort of the focus has been on finite symmetries. What about continuous symmetries, space-time symmetries, and sort of really explore the full scope of these anomalies, because once we understand the anomalies, it'll give us new handles on QFT or G-flows as well. Okay, thank you for your attention. I know what the question is. What does it have to do with string theory?
I'm going to ask an easier question. I'm kind of curious about your point of space-time symmetries, your work too.
Ah, yes, of course, yes.
Can you reveal something about
Yes, this is a thing that will appear, well, hopefully in a few days. So this is with Nicola Dondi, who's somewhere here in the audience also, and Fabio, Iñaki, and Hotat. So the idea is the SymTFT is essentially you gauge the symmetry into bulk. Well, we've seen that before. It's like holography-ish. Yeah, that's why condensed matter physicists call it topological holography. But it's not quite. So even if you look at space-time symmetries, continuous ones, what you get is not necessary, right? All I want to model is the global symmetries. So then you can ask, what is it when you gauge into the bulk, this space-time, say, Poincare or conformal symmetries? And what you get is something that in low dimensions is just going to be like gravity, 1+1D gravity. It's going to be exactly a BF theory for the symmetries, and that's the SymTFT. But in higher dimensions becomes more distinct from it, but there's a clear connection. So essentially, what this allows us to do is study symmetry breaking of, conformal symmetry to Poincare, these kind of things. In fact, stuff that Fiona, who's sitting right next to you, has studied in the past as well. So it connects that kind of direction to the symmetry TFT. And I think there are many applications following from that, but at the moment it's just about sort of writing down what is the SymTFT and what are the boundary conditions. Yeah. So. No questions. Okay. Boris.
Can you just comment on the challenges in extending to continuous symmetries?
Well, the first question is how are you gauging? Are you gauging a flat or with actual dynamical gauge fields, right? But here we're just writing down BF theories for continuous symmetries. And that's been done also in these papers here, again by Nicola, and also I think Nikhil is in the audience, who've written down for internal symmetries, the SymTFTs for, say, a U1 or a non-abelian group. So it's a bit more messy because there's no structure like a category that we know, but then also it's mostly not non-invertible. So it's a little bit, it has different challenges.
There's no full classification. There's no full classification.
Of what? Oh, boundary conditions.
Symmetry breaking patterns of these generalized.
Yes, so I think, sure, but here these are not necessarily generalized, right? They're just U1s, SUNs. So it's interesting to ask what you can actually concoct. So there was a recent paper in 2 dimensions by Jung-Cheng and others where they had non-invertible space-time symmetries in 1+1D. So one could consider such things. There are also finite non-invertible symmetries, of course. So in condensed matter, you could have translations that are non-invertible. But they're slightly different. So you're asking about continuous. So in continuous context, these are usually just vanilla group symmetries. Okay, thank you.